to some degree, how we're going to recognize if at least some sort of equations are well, or will lead to well-behaved solutions. So we started with the first order system. So if we imagine an equation of motion given by this, the time derivative of a vector u, so it doesn't have to be a single unknown, it could be just a vector of unknowns, equal to kind of several matrices, one per each direction if now we're space-time, acting on the derivative or contracting with the derivative, which then acts on the vector of unknowns. To try and understand or get a simpler algorithm to recognize when this is going to be well-behaved, we introduce a Fourier decomposition. So we imagine that u is expressible in terms of an arbitrary number of plane waves, which when combined we can write any solution. When we put this in here, we end up with an equation for the time dependence part of the function. This is where we have the space part, dependence of the function u, and this is the time dependence. And we can write this way. And then we said that the system was going to be well behaved, and for that we introduced the concept of strongly hyperbolic. If the eigenvalues of this matrix were real and linearly independent. We'll see, I'll give you a very precise example in a second, or motivation why we asked this. But to do that, let me start with a very simple equation. So this is just the advection equation. So the time derivative of the function u multiplied by a lambda, this is a coefficient, times the derivative of u. It's just one equation for the function u in one dimension, so it's the simplest possible one. We use exactly the same decomposition I use here. I imagine that u, I can express it in terms of a plane wave solution into e to the I omega x times some function that we want to determine. Once we put it in here, following that notation, I can write it this way. It's I, so it comes from the e to the I omega x. Then I have omega, which I'm going to write it as omega divided by its magnitude times its magnitude times lambda times u. And what we're trying to solve is for u hat. When we do that, that's a straightforward iteration, because we're assuming the lambda is a constant. And as a result, we have u hat is just e to the I omega, if you want, omega lambda t. And now we can see easily a condition for this function to be bounded in time for all time, which is that this lambda better be real. If lambda had an imaginary component, when we take the norm of this, so if it is real, we take the norm of this, we'll just get 1. And of course, we already had a 1 here in the space-dependent part. But if lambda had an imaginary component, all of a sudden we're going to be picking up an exponential. Of course, you might say, well, it might depend on the sign of that imaginary component, but no one has told us yet where this omega is going to be positive or negative. So we're going to end up having something of the form e to the omega t, which for even when for negative omegas, this would be with whatever imaginary part we have, imaginary part of lambda we have here, even though one sign will be decaying, the other sign will be blowing up. So in essence, this is what this condition for hyperbolic equations boils down to. So let me just kind of give you a simple argument of why is that we keep going after this kind of conditions. So suppose now, going back to this with changing slightly the notation, we have an equation, and let me, for simplicity, say it's dx of u. But let's ignore everything else. I'm going to relax, in this case, the assumption that A has constant coefficients. So this might depend on time and space, but I'm going to assume it doesn't depend on U for the time being. But A is a matrix, and U is our unknown of our vectors of unknowns. So now hidden in this condition that lambda is real, and we have a complete set of eigenvectors, is the idea that if we have a complete set of eigenvectors, there exists a transformation, say, given by some matrix T, such that T to the minus 1 times matrix A times T is nothing but a diagonal matrix. And it's a diagonal matrix with eigenvalues given, with entries given by the eigenvalues. So now I can use this to try and rewrite this equation. So it is also true that T to the minus 1 T is equal to the identity. So I can put the identity in a few places. So I'm going to choose to put it here. Let me do it in the opposite order. T to the minus 1. So I put an identity there. And I'm going to put another one here. T to the minus 1. I can also choose to act with T to the minus 1 on the left. So I'm going to multiply by T to the minus 1 here, and T to the minus 1 there. So let me now combine things in a particular way. So I'm going to have T to the minus 1 u comma T equal. This T to the minus 1, I'm going to have acted on the T here. So this will give me the identity times T to the minus 1 times A times T. I'm going to put this a little bit to the side, T to the minus 1 dx of u. So now this thing is our diagonal. So let me just put it here explicitly. And we have T to the minus 1 u comma T and T to the minus 1 u comma x. And the last thing we can do is just group this together and notice that, say, T to the minus 1 on whatever derivative we care. So let me just put an A there. We can write as T to the minus 1 u A minus, at least formally I can do this. But with that, now I can rewrite this equation. Let me define a new vector, v T to the minus 1 of my vector u. So then the first equation happens to be v comma t. So the left-hand side is v comma t minus something where u appears undifferentiated. So I'm going to shove it to the right-hand side and just bring it back in a second. Then I have the diagonal there. And now again I have T to the minus 1 u comma x. I can use that formal expression and write it as v comma x. And then I have here plus undifferentiated. So undifferentiated u terms or v terms. But what we arrive to here is nothing but a collection of equations of that type, of advection equations. So this is just a collection. So we render our original problem into just a problem where we have a collection of the simplest possible equations in first-order form we can think of that are hyperbolic. And so we go back to solutions of that type, where we ask the lambda to be real, otherwise we would have an unbounded growth, and this is what it is. So the requirement of a complete set of linearly independent eigenvectors is implicitly telling us this. it comes from this as well, to the desire to know that we have a whole bunch of simple advection equations. So with this, we have a simple rule, which is a sufficient condition for well-posedness, which is extremely powerful. So notice that I keep forgetting and not talking about the undifferentiated terms. I just throw them to the right-hand side. This equation with lambda being real is so robust that the properties we infer are not going to be changed when these u terms are thrown in. This is as opposed to the case of the example we gave, where this matrix was not diagonal, was a Jordan form with elements of the diagonal, where even though we could kind of obtain a growth, a bound estimate of this part that was not too violent, the very simple addition of simple terms that were undifferentiated turned a linear growth, say, into an exponential growth. So that's why we regard this as very convenient. It might be too strong, but it tells us that for general cases, these equations we have are going to lead to well-behaved solutions. So is that clear? So this is for first-order systems, first-order derivatives. We can extend this to second-order derivatives. Of course, the first way of doing it, which is the simplest way, if we have an equation now of the form this way. So we can have an equation that has second-time derivatives, a contribution that is second-space derivative, and another contribution that is the product of first-space derivative with first-time derivative. So an easy way to use up everything we've learned so far is come to these equations and introduce as many first-order variables as we need to render this equation into first-order form. So that we can always do. We can say, for instance, let me just do it explicitly here. Suppose we have this equation. We could say, well, introduce a function f to be u comma x. Introduce the function g to be u comma t. In terms of these variables f and g, we can rewrite our original system in the following way. G comma t equal f comma x. So this is nothing but u comma tt equal u comma xx. We also have the condition that the time derivative of this one has to be equal to the space derivative of that one due to the commutation of derivative. So the other equation is f comma t equal g comma x. And finally, if we want to get u, this is that equation. So armed with sufficient number of first-order variables that are introduced, we can rewrite a second-order system in terms of a first-order system. And once we're here, we can just use the definitions we have. So that's straightforward. But very quickly, things get very, very cumbersome. If you imagine in the case of Einstein's equations, we have, we wrote the equations like, even though we said that we're going to tell us, or we're going to show that this is not a good system, but we wrote equations of the form dt of gamma ij equals something, dt of kij equals something, and here we have the Ricci, for instance, and the second derivatives of alpha. So we would have to do, for every second derivative here, we'd have to introduce variables which contain the derivative of the matrix gamma along the x, y, and z direction. So our original 6 variables here add 18 more variables. So very quickly we end up dealing with too many variables, too many functions to solve for. But that's okay. We can still use the definition, and you can find papers where the hyperbolicity has been gauged in terms of the first order form of the equations. Let me give you at least formally what we can do if we want to analyze things directly in second order form. But in this case, quickly, the first order results will come in. So suppose we have that. We can take the same ansatz and look for solutions in plane wave form. So when we put this into this system, we arrive at an equation for u hat, which is determined by the following relation. So we have a result that says a necessary condition for well posedness. So this quantity, so again, if I'm trying to solve this equation such that this function has bounded norm, just in the same way we would have derived this condition, is that this matrix has real eigenvalues for exactly the same reasons. Of course, let me know, how is it that that's a necessary condition? It's not sufficient. The next one is related to the nature of the eigenvectors. Then it becomes a little more difficult. And for that, the easiest or a clean way is to kind of introduce a first order form, a first order reduction. So let me introduce the following. So I introduce a new variable v, which will keep for us the time derivatives, and it's absorbing this I omega that is sitting here. So then we can rewrite the system now in this form. So now if we stare at it, we end up with a system with respect to the now vector and large vector uv is a matrix times the vector, and this is very much what we had before for the first order case. And so now the sufficient condition is that this P has real eigenvalues and a complete set of eigenvectors. And then if you have a particular case where, say, this P1 is 0, where you don't have in the right-hand side the product of time derivative and space derivatives, then there is a simpler version that says, well, you want the P0, so let me just write here. So if this P1 happens to be 0, then by just identifying P0, we can conclude that the system is going to be strongly hyperbolic if there is a complete set of eigenvectors. Notice that here we're also asking that P0 has eigenvalues that are real. So it's the first time, and positive. This is the first time we're choosing a sign. But the reason for that is obvious by the nature of the equation. So let me just also illustrate this with this equation. Again, if we plug in our ansatz, because of, let me imagine I can put a lambda here. So this lambda, this will bring two derivatives. This will be I omega squared times u. So this will be minus lambda omega squared u. And now when we take the square root, sorry, u comma tt. Now when we try to find the solution of this one, we're going to be taking the square root of this whole thing. If lambda is not positive, so if, let's say if lambda is real and positive, the result of us taking the square root of this one will give us plus minus I square root of lambda omega squared, which gives us now something that has bounded norm. But if lambda were negative, then this would be positive, and the square root will give us a real function, which will now be unbounded. You see that? So let me just do that if you want explicitly. Imagine that we put an ansatz for u, this u, we e to the st. When I plug this in here, we're going to have the equation, and the equation is s squared is minus lambda omega squared. And then this will have solutions that are purely, S will be so S will have solutions that are purely imaginary and therefore a bounded growth, I mean a norm that is unitary, only if this lambda is positive. So let's use this machinery a little bit to try and understand the ADM equations.
Luis, just
yes.
a question to see. That left-hand side of the equation should be omega t, and two time derivatives?
Which one?
Hand side, the first one.
This one?
Yeah.
Yes, sorry.
Okay.
Yes. This is how this kappa squared comes. Mm-hmm. I assume that the solution to u, well, what I call S over there, is written as e to the kappa t, and then you're trying to make sure that this kappa has the right sign. So the ADM system is the system we wrote the other day. Let me just quickly try and simplify in a significant way to try and make contact with this and then have a conclusion. So let's simplify a few things. So remember one thing we did, just going to write here, is to, I'm going to write again or draw again our decomposition. We decompose the space-time in a sequence of spatial hypersurfaces. We induce an evolution, and then just let me make a few more comments. If this is our normal vector, we might have a flow of time defined that way. And this did mention that there is a difference between the flow along the normal direction and the flow along our time coordinate, which is kind of relating one and the other one through the lapse and the shift. You might have said, well, hold on, why do we go to the bother of defining or having this lapse and shift when we could just define a flow along the normal direction, which is a time direction, and that would be fine. That will correspond to having chosen alpha equal to 1 and beta equal to 0, the vector beta. But we also have to we want to be mindful that we can have pitfalls. So imagine that, well, I can give the example here, but let me just be a bit more extreme in my example. Imagine our foliation at some point looks like this. And we're trying to go to the next hypersurface. Well, the normal at this point points that way, but at that point points that way. So what we have, if we try to follow the evolution along this normal, eventually is that we're going to get to a point where it has two different labels, but the point in the space-time is the same. So we're going to lead to a coordinate singularity. So that's the reason we try and maintain this freedom, which we encoded in the lapse function and the vector and the shift vector, to try and help us prevent situations like that. Because the foliation might be perfectly fine, might look exactly like this, and following the normal direction would be counterproductive. So in that case, we might find that maybe a shift that pushed this coordinate that way and this one that way, and that's the right or a more convenient flow of time that we would have to choose. Also, all this kind of this decomposition we did, let us write the system in a way that while we lost the general covariance, the general four-dimensional covariance of the theory, we try to maintain as much as possible at least three covariance. So everything on the hypersurface was projections, and we derived things with respect to tensors intrinsically defined on that hypersurface or projected onto a hypersurface, but we maintain covariance. So only when we try to do a specific calculation, we do want to bring specific coordinate choices. If not, it's very general. So now I'm going to take some choices so that we can do the analysis. We're going to start with this one, lapse equal 1, shift equal 0, which we argue that if we have a foliation that curves in a region sufficiently, that might be a very bad choice. We're going to look to do the calculation in a very specific setting. We want to do the calculation around flat space-time. So we're going to consider flat space-time, the metric gamma ij. We're going to assume is simply given by delta ij plus some small perturbation. And now, sorry, I'm going to introduce h again. Now, h is not going to be gamma. It's just the small perturbation over flat space-time. I'm going to put this again into the equations, the ADM equations we wrote, when we're only going to care to leading order, to epsilon order. If we find the problem already in epsilon, it won't be possible to fix it with an epsilon square contribution. So what we're after is to show that even in this very simple setting, over flat space-time and keeping the equations to linear order, we're going to have a problem. So first, remember the definition of the extrinsic curvature Kij in terms of the d derivative. So this was roughly given by this, and then there were terms, d derivatives along beta, bk gamma ij. But we have chosen the lapse to be 1 and the shift equal to 0. So then for that case, the extrinsic curvature is just simply the time derivative of the gamma. We also had an equation of motion that says dt of kij equal a whole bunch of terms, but because the dt of the extrinsic curvature is the same thing as the second time derivative of gamma ij. Right. So I'm going to use the second definition, the one with respect to the second order form, to arrive to the result in a simpler form without having to introduce lots of first order variables. So now let me just write what you get when you consider the equation of motion for the extrinsic curvature under these assumptions and keeping it to linear order. So this is second time derivatives, or dtt gamma ij is equal to so that's if we leave the lapse function, but we say we're taking it to 1, so it's going and goes this way. So that's in general. If we now use this expression and keep only the linear order term, this reduces to the following. But now we can combine and take the trace with this delta ALM and rewrite this right-hand side in the following way. So the first thing we notice is the following. So this thing is just simply the flat space-time Laplacian. So it's a second derivative. Let me write it this way. dk of hij at where there is a summation implied in k. So I can do this. All right. So this thing is a familiar wave equation, or is a whole bunch, 6 wave equations, one for each component of hij. And then this is the rest, these extra terms in here. The first term we see in here is this is nothing but the momentum constraint. If we write the momentum constraint, this is what we will get. If we assume that our initial data exactly satisfies the momentum constraint, we can get rid of that one. But we still have an extra piece. This di dj of h. So we can now try and make contact with this result. So the first thing we notice that nowhere in the right-hand side we see a combination of time derivatives multiplying space derivatives. So we're in this simpler setup where this P1 is 0. So we just have the P0. And we can just check using this result, what is it? So the easiest thing would be take a single direction. Just imagine the waves that we're looking for is just a plane wave in the x direction, a whole bunch of plane waves in the x direction. So of this, only x derivatives survive. If the test fails in that simple case, we know it's going to fail in general. And when you look at that, you find out, I'll leave that as an exercise, that this system will have the eigenvalues, so the P0 you obtain as a result has eigenvalues. We'll have one eigenvalue equal to 0, and then this is just 1, and then we'll have 5 with eigenvalue 1. And it's completely degenerate. And so it fails to satisfy our conditions for strong hyperbolicity. The good news is that the eigenvalues are positive. Are real. If they were not real, then we have a system that's completely ill-posed. This is one of those cases where we have something that if there were no extra terms, we might be able to bound the solution with a linear or polynomial growth, not an exponential. But we do know that there are a whole bunch of extra terms, which will turn that into an exponential growth. So that's the problem with the ADM system of equations. Even in the simplest possible case, we arrive at a system that has not ideal properties. There is still some freedom, because you might wonder, well, how about this choice? I mean, this one, okay, that's the physics. That we're talking about asking the behavior of a small departure or a small perturbation in flat spacetime. That's justified. That's the physics. Here we have chosen the lapse and the shift in a very specific way. You can argue, could this be the source of the problem? And the answer is yes, it's partially the source of the problem. It's not fully the source of the problem. You can remove some of these degeneracies by a judicial and better choice of the lapse and shift, but that's not enough. And will describe tomorrow how we go about doing it in a different formulation of Einstein's equation. Then you have a homework for a different formulation of Einstein's equation where you see the freedom here is explicitly taken advantage of or used to try and remove some of these terms. In particular, I can kind of anticipate that if this term were not there, we just mentioned we have a whole bunch of wave equations. And here things are perfect. There's nothing wrong with this. We would have eigenvalues given by 1 or minus 1, the propagation speed of light. And we will have a complete set of eigenvectors. So in some sense, this is the offending term, and we have to do something with it. And that's going to be part of Will's description and what you might see later on in your homework. And part of it involves using this freedom and also using the constraints to your advantage. Because in particular, we use it here. Right? I said, no, this is the constraint. If we assume it's satisfied, it's gone. Well, but when we try and this concept of strong hyperbolicity basically is assuming or is trying to assess the robustness of the system of equations you have and the solution it produces upon arbitrary small variations and perturbations of the initial data, which include perturbations that violate the constraint. So one option we have said, well, not to assume that this is satisfied, but at the analytical level, we know that this equation shouldn't change if I add here the momentum constraint. So I can always add the momentum constraint with the right sign such that it cancels this term from the get-go. So this is going to be part of the exercise. Exploiting the freedom in the coordinates plus exploiting the possible ways of adding and subtracting zeros to try and modify offending terms. You had a question?
Yeah,
So this subject is huge. As I said, it was the source of nightmares for a very long time in the understanding of the nonlinear behavior of the theory. But by now, there is a rather well understood way forward for these equations. And there is a beautiful review by Manuel Tiglio and Oliver Sarbach. If you want to go read everything you would like to know, it's actually very well explained there. The last thing I wanted to show in a very kind of quick way, but just so that you understand or you see more explicitly some of the things we've done, is just some set of Maxwell's equations. Yes, go ahead.
Was this realized that lapse 1 shift 0 was unstable before doing evolution? So it was
no,
realized before, or
this observation was always there, right? So these people knew, but that even in such a simple case where you say, well, I started with a foliation where this doesn't happen, because you say, well, why would this foliation have that behavior? You can choose a different one, at least initially, that doesn't have that. And if there is not enough of strong perturbation, you don't think you're going to curve it enough. So people were expecting, at least in some cases, this should work. So in a sense, the history went more like people thought these were fine. They actually, this system is perfectly fine in the applications that were at that time. So because this degeneracy, if you now assume that there are symmetries in your problem, like in spherical symmetry, it's gone. Now you have a lot fewer variables here. And when you analyze the structure of the resulting equations, those are fine. So there was a lot of evidence, quote unquote, that this system would work in special cases. It was when people started going into three-dimensional simulations, things were not working, that everything was kind of revised. And in the course of that revision, then these things started appearing. Even though they were known for a few decades in the applied mathematics community, it hasn't been transferred to the rest of physics, if you want. And I would say even today, this is the example I was doing the other day, I can point to systems of equations that are commonly used in astrophysics that are pathological from this point of view. But yet you identify what the terms are. So for instance, you have this term, and for whatever reason you know that this has to be 0, then you could try and control it. And as I said, what you want, and numerically this is what you excite, is violations in all possible variables. So even the constraints are slightly violated. So if say the offending term was this one, then people came out with very, very clever and I would say complicated schemes to ensure that this would be 0 regardless of the evolution. So the variables themselves could have huge errors, but the combination appearing, say, in a term like this was guaranteed to round off level. So then with that, you're able to remove the offending term and then move forward. But if you recognize that the offending term is this one, and you have sufficient freedom in your system of equations, then you might remove it altogether, and then you don't have to worry about that. Yeah. So that's a good comment. So Paolo was asking yesterday, well, how do we know? Because I'm saying I'm playing with maybe adding the constraints or with coordinates to try and help this problem. How do we know in general? Well, in general, we really don't know. If we have a system that is completely determined, then we don't have much freedom. But in cases like Einstein's equations or Maxwell's equations, we have constraints. The system is overdetermined in some sense or underdetermined in another one. So we're trying to solve for, say in this case, 6 unknowns, but we have 4 constraints. And we have that extra freedom. We can trade some variables with others. So the system is not, when we write a system of equations out of Einstein-Hilbert action, the system of equations is not unique. So we know that's the case. And so we have to explore where we have any freedom. because I was just telling you, so the ADM doesn't have the right properties, but that doesn't mean the theory is sick. It means that the way we render the equation of motions for that theory is sick. So you have to be careful not to conclude that the theory necessarily is sick. We conclude the equations derived for that theory are sick. If we don't have any freedom, then we'll be saying that the theory is sick. But if we have freedom, we have to work harder. So let me just try to go back to a simpler setting to motivate a bit more, or just make more explicit some of the things we've done. So in this 3+1 decomposition. So I mentioned earlier today that one of the things we did, or we were doing when we introduced all this extra structure to do a 3+1 decomposition, was to try to break the covariance of the 4D spacetime into something that was still respecting or keeping some of the covariance explicit. And we chose, in this particular case, to keep the covariance in the 3D spacetime. That's how we introduce many concepts. So suppose, for the sake of the argument, we're thinking of Maxwell's equations, which we know in covariant form are written this way, and something similar for the dual. I'm just going to stay with this one, because I'm not going to cover the full set of Maxwell's equations. But let's say we have a Faraday tensor, which is a covariant antisymmetric two-rank tensor, whose divergence is linked to the current by this equation. So let's see what some of these tools that we introduced to do the 3+1 decomposition would allow us to do. So in particular, we can say, well, let's try and decompose this Faraday tensor into quantities that are naturally well adapted to this 3+1 way of thinking. So the obvious thing is to say, well, one thing I can do, I have two indices. So obviously, at least at formal level, let me just write it this way, I can do the following. So I can say, well, FAB has two legs, and I'm going to project each leg either parallel to the vector n or orthogonal to it. And when we do that, that's something that lives on the hypersurface. So we have CD, HCA. AB. So I can say, well, this is by definition I can do that. So here I projected F along n, both components, 1 and 1, the opposite, and all in the hypersurface. This is the same thing we did when we discussed the preservation of the constraints in the Einstein equations, right? We wrote the full Einstein equations with things that were totally projected to the hypersurface, 1 and 1, or both along n. So of course, in this case, because F happens to be an antisymmetric tensor, this is 0. And out of this, we can define the following vectors. I'm going to just introduce them first and then give you the expression. So we introduce the vector E and B by contracting the F with an N. So that's what we have, one here and another one there. This is why it shows up in here. Recall again that when we contract n with b here, if you think of at least locally in space n just being ddt for the sake of the argument, this picks the t component. This A cannot have a t component, so this can only be a special index. And if you remember the decomposition of the Faraday tensor, then the ti components give you the electric fields. And this is the same thing with respect to the dual tensor, this dual Faraday tensor, and it's doing the same thing. If you undualize it, then this will, what it's going to be giving you is the component of the magnetic fields are in the ij part of the Faraday tensor. So let me just try and quickly derive one of, or at least give you the basics of deriving Maxwell's equations out of this using this decomposition, and then try and recognize the standard Maxwell's equation. So let's consider the following. Consider this one. And we're going to have the right-hand side, but we can deal with the right-hand side in a second. Let's consider what happened with this. I have a free index, B, if I contract along n. So just as we did the array, I'm going to bring the n inside. And I bring the n inside is because the moment I do that, I can bring the electric field explicitly. So this would be grad A, FAB, NB, minus FAB, grad A, on NB. So when we take n in here, I'm multiplying FAB by what, NB? So when n hits this n, I get a minus 1, that gives me E. When n hits E, it gives me 0 because of the antisymmetric property of FAB. And when n hits E, I'm also going to get a 0 because this E, this is a 3E, this is just a purely spatial one, so I get a 0 as well. So the first term is just simply grad. This one, you have to remember what we did for grad of n. So we're considering the fully spatial projection of this grad. We have the extrinsic curvature. If we're considering orthogonal to it, then we have the acceleration. So this is FAB times extrinsic curvature minus the acceleration. So this is grad A minus. Now we can use some useful properties. We proved that this extrinsic curvature tensor was symmetric, but F is antisymmetric. So the product of these two is 0. I only have this one. Then FAB contracted with NA gives us the electric field, and then the acceleration. So this gives us. And we also need to remember in this definition here, n is contracting the second index. Here, n is contracting the first index, so I can flip it. I can do the A, change the plus sign. And now this gives us minus EB, AB. So the product of the electric field and the acceleration is here, and then I have that one. So the right-hand side, NA, GA, well, let's define that to be rho. or like with a minus sign. So then that would give us the charge density. So we're almost ready to say, oh, we have re-derived the constraint of the charge density, but we have to be careful. This is still the covariant derivative of the full spacetime. We want to write with respect to the covariant derivative of the free spacetime. So let me just go through that, and we'll stop there. So grad A, EA is the same thing as GAB, A, EB. And in this business of trying to write things in covariant form and projecting, you always end up playing this trick, bringing metrics explicitly, decomposing in terms of the projector plus n, and then recognizing the contribution of different terms. So this is the same as GAB, but GAB was gamma AB minus NA NB. Now, gamma is a projector of the covariant derivative, and E is, by definition, a spatial tensor. So the first term gives us EA, which is the term we were looking for. Now, this is the divergence on the hypersurface of a vector that belongs to the hypersurface. We still have to take care of this extra piece. And I'm going to do the same thing once again. Oh, sorry. I'm going to pull this n inside and then use Leibniz to correct what I just done. But now this is a contraction of the electric field that lives on the hypersurface with a vector that is orthogonal to it. So that's 0. And then this piece is E contracting with the acceleration of the vector n. And notice that then that means that this is the divergence of E on the hypersurface plus E contracted with acceleration minus E contracted with acceleration, so we obtain and so we have now derived the constraint equation, and just as we did before with the Einstein equation, so we have an equation, we project it along ends. Remember, the Hamiltonian constraint was the Einstein equation projected both legs along n. The momentum constraint was one leg along n and the other one orthogonal to n. That gives us the constraint. So here we only had one free index. The contraction with n gives us the constraint equation. And now I'll leave us an exercise, give it a try. You can come and ask me. If not, you can check different books. This is encounter there, but if not, just come and talk to me. If you consider the following contraction, so take again and contract, the free index with H, say BC, you're going to find out of this the evolution equation. So you have to find the time derivative of the electric field is related to the curl of B and a current. So I'm not going to go through that because of time, but it's exactly playing this kind of games. So try do it. It's actually after doing it twice, the third and fourth times are fun. From there on, it's annoying. So maybe go try to hit that third and fourth time with the Maxwell's equation.
And for the magnetic field, it's just with the dual of the
yeah. You can do it in two ways. You can take the dual and then everything follows exactly the same way. Or if you want, you can take that expression of FAB and then consider the Bianchi identity, the fully anti-commutator derivative. Also, you can get it from there, whichever one you prefer. And of course, the projection, so that you recognize out of it the constraint and the evolution equation. Okay.